Welcome to lecture 10. This is the final lecture in this course, um, Introduction to Information Theory Part 1, offered on the IEEE platform. I'm your course instructor, Sachin, from the ECE department at the Indian Institute of Science. Last lecture was a summary lecture where I summarized all the topics we covered, mostly chapters 2 and 3 of the textbook information elements of information theory by Thomas and Cover. This lecture will we actually had a problem solving session before where I solved 5 problems, I think. This lecture will solve some more problems and that will be it for the course. We'll start off with problems from lecture 2, chapter 2. We had solved 5 problems, I think. We'll start from the sixth problem. I won't be able to solve all the problems in just 2 hours. I'll solve just a few. The rest you can go and try it on your own. Let me just see which problem I had. Okay, I had solved 5 problems. So we have to start from the sixth question. Conditional mutual information versus unconditional mutual information. Give examples of joint random variables x, y, and z such that a I of xy given z is less than I of xy. Part B, you have to give examples such that give an example since I of xy given z is greater than I of xy. Remember that um, entropy cannot increase, conditioning cannot increase entropy, but for mutual information, conditioning can increase entropy. So the solution is consider XYZ that form a Markov chain from 2.8.1 theorem 2.8.1 says that in this case, if XYZ form a Markov chain, I of xy is greater than or equal to I of xy given z with equality if and only if I of xz equals 0. are x and z are independent. So we have that x be a fair binary random variable, and let y is equal to x, z is equal to y. This case I of xy is h of x minus h of x given y is at h of x. So x is equal to y is equal to z. So I of xy is nothing but I of xx, which is the self information. So which is equal to the entropy. And entropy of a binary random fair binary random variable is one. But I of xy given z is h of x given z minus h of x given yz, which is zero because x is equal to y is equal to z. So given z, you know both x and y. So z determines x and y. Therefore, h of x given z is zero. H of x given y z is also zero. So y of x y given z is zero. Therefore, I of xy is greater than I of xy given z. So x and y for the other case, x and y be independent pair binary random variables, and let z is equal to x plus y. We have I of xy is zero because x and y are independent. But I of xy given z is h of x given z minus h of x given y and z. Now h of x given y and z is zero because x is z minus y. So x, y and z together determine, but h of x given z is not zero. What is h of x given z? H of x given z is equal to, these are binary random variables. So z can take the value 0, 1 or 2 because x can take 0, 1, y can take 0, 1. The sum of x and y can be 0 plus 0, 0, 0 plus 1 or 1 plus 0 both will give 1 and 1 plus 1 will give 2. H of x given z is equal to 0 plus h of x given z is equal to 1 plus h of x given z is equal to 2. But if you say z is equal to 0, that's only possible if x is equal to 0. So there's no uncertainty if you know z is equal to 0. So 0 plus, if you know that z is 1, that means either x is 0 or x is 1. Both are possible. So both are equally likely because x and y are independent and um, probability p of xy is equal p of 0 1 is equal to p of 1 0 is 1/4. So p of z is equal to 1 is p of x is equal to 0, y is equal to 1 plus p of x is equal to 1, y is equal to 3, which is half. And so given z is equal to 1, you can work it out yourself, but uh, this x is distributed as a binary, fair binary random variable again, given z is equal to 1. So x can be 0 with probability half and x can be 1 with probability half. So in that case, h of this is 2 times half log 2, which is nothing but 1. Sorry, it's half log 2. It's 2 times, so this is 2 times half log 2 plus again h of x given z is equal to 2 is 0. This is just 1. Therefore, I of xy is actually less than I of xy given z. So conditioning actually include the mutual information. Next question is on coin weighing. Suppose that one has n coins, among which there may or may not be one counterfeit coin. If there is a counterfeit coin, it may be either heavier or lighter than the other coins. The coins are to be weighed by a balance. Find an upper bound on the number of coins n so that K weighings will find the counterfeit coin, if any, and correctly declare it to be heavier or lighter. What is the coin weighing strategy for K is equal to 3 weighings and 12 coins? So I'll only solve the first part of this problem and leave the second part to you. Second part is a much more difficult problem than the first part. It will take a lot of time. So first thing to note here is we are weighing the coins by a balance. So we are putting some number of coins on left side and some number of coins on the right side. And the only way we get any useful result if we put the same number of coins on both sides, right? Otherwise, uh, the if you put more coins on one side, obviously that will weigh uh, more than the other side. So we'll put equal number of coins on both sides, and then uh, in that case, there are three possible situations, right? Either when every weighing, so they say you have k weighings. So in every weighing, you can either have equal, in which case both sides have the same number of same weight. In which case there couldn't be a counterfeit coin in that weighing. So if you have 10 coins and you put 5 coins on both sides, and you get equal weight, then that means there are no counterfeit coins in that batch, right? Or you could have the left side is heavier or the right side is heavier. There are three possibilities in each weighing. So each weighing has three possible outcomes. Equal weight, left side heavier, right side heavier. That means initially you split the coins into two groups. If there are even number of coins, you can equally split it. If there are odd number of coins, you remove one of the coins and weigh them. Split the rest of the coins into two and weigh them. So they can be when you weigh the two groups with the balance, both groups can have the same weight, or um, either of the two groups can have heavier weight. So each weighing can have three possible outcomes. K weighings can have 3 power k possible outcomes. For n coins, there are 2n plus 1 possible states, right? One of the n coins is heavier, and this coin can be any one of the n coins, so there are n possibilities. One of the n coins is lighter, and all coins are of equal weight. So there are n ways in which a single coin can be heavier, there are n ways in which a single coin can be lighter, and there is only one way in which all coins weigh the same. So there are two n plus one possible states for the coins. Since we have 3 power k possible outcomes for the weighings, we can distinguish between at most 3 power k different states. Therefore, 2n plus 1 must be less than or equal to t 3 power k, or n must be less than or equal to 3 power k minus 1 over. So from an information theoretic perspective, each weighing gives log 3 base 2 bits of information at most, because there are three possible outcomes for each weighing. So the most information for a random variable with three possible outcomes is log is the uniform distribution, which has the entropy log of uh, what is it mod of script x. Since overall there are 2n plus 1 states overall, which implies maximum information or maximum entropy is log of 2n plus 1 base 2 bits. Hence, we need at least log of 2n plus 1 base 2 must be less than or equal to k times log 3 base 2, or k must be greater or equal to log of 2n plus 1 over log 3. So that is total amount of information is about log 2n plus 1 bits. Each weighing can give you at best log 3 bits. So you need at least k weighings to give you uh, k weighings to give you k log 3 bits at most. Right? That's assuming the weighings give you independent information. Otherwise, you will get even lesser uh, bits of information. So at least you need log 2n plus 1 by k log 3 weighings. Part B is homework. It's a difficult problem. Next question. An urn contains R red, W white, and B black balls, which has higher entropy. Drawing K greater than or equal to two balls from the urn with replacement or without replacement. If we consider the case with replacement, the conditional distribution of each draw is the same for every draw. So xi is red with probability r divided by r plus w plus b. Probability that the ball that is drawn as white is w by r plus w plus b. Probability that you draw the ball drawn as black is b over r plus w plus b. H of xi given xi minus 1 up to x1 is nothing but h of xi, because before each draw you replace the ball, so each draw is identical and independent. And this will be log of r plus w plus p minus r over r plus w plus b log r. Actually, this is r over r plus w plus b minus r over r plus w plus b log of r over r plus w plus b. But we separate log of r over r plus w plus b into log r minus log of r plus w plus b. And minus w by r plus w plus b log w minus b by r plus w plus b log of b. And so, okay, maybe I'll write down the steps and then I'll realize it later. So actually what we are doing is r by r plus w plus b log of r plus w plus b by r plus w by r plus w plus b log of r plus w plus b by w plus b by r plus w plus b log of r plus w plus b by w. That's h of xi. Then we split this log of r plus w plus b by r as log of r plus w plus b minus log r. So we get r by r plus w plus b into log of r plus w plus b minus log r. Plus similarly w term and w term. Then you group the log of r plus w plus b terms and you'll get r over r plus w plus b plus w over r plus w plus b plus b over r plus w plus b, which will be r plus w plus b divided by r plus w plus b, which is 1. And the other terms will be minus log r into r plus w plus b minus log w into so on. So that's the entropy of each draw with replacement. Now, if you do without replacement, h of xi is h of h of xi given xi minus 1 etc. x1 is less than or equal to h of xi, which is equal to this is the unconditional entropy of the ith draw, which is actually the entropy with replacement. So if we don't do without replacement, there is some conditioning. The conditioning is whatever balls were drawn in the previous uh, I minus 1 draws, so, which will always be less than or equal to h of xi. So we can, from this, we can say that the entropy of drawing without replacement is lower. Next question 4. A function rho of x comma y is a metric if for all xy rho of x comma y is greater than or equal to 0. That's the first condition. Rho of x comma y is equal to rho of y comma x. That's the second condition. rho of x comma y equal to 0 if and only if x is equal to y. Final condition is that rho of xy plus rho of yz is greater than or equal to rho of xz. The question is to show that rho of xy is equal to h of x given y plus h of y given x satisfies the first, second, and fourth properties. And then if we say that x is equal to y, if there is a one-to-one function mapping from x to y, the third property is also satisfied, and rho of x comma y is a metric. Part B is verify that rho of x comma y can also be expressed as rho of x comma y equals h of x plus h of y minus 2i of xy h of xy minus I of xy equal to 2 times h of xy minus h of x minus h of y. I will only solve part A, part B verification you can do it yourself. We know that h of x given y greater than or equal to 0, h of y given x greater than or equal to 0. Therefore, h of x given y plus h of y given x is greater than or equal to 0. That is, rho of xy is greater than or equal to 0 for any random variables x and y. Rho of y given y comma x is h of y given x plus h of x given y, which is equal to h of x given y plus h of y given x, which is equal to rho of xy. So it is symmetric. Rho of x comma y is equal to 0 implies h of y given x must be equal to 0 and h of x given y must be equal to 0 because both are non-negative quantities. H of y given x is 0 implies y is a function of x, and h of x given y is 0 implies X is a function of y, which implies there is a reversible function between x and y. So how that comes about, you have to go and check in calculus or algebra. Uh, y if x is a function of y and y is a function of x, then there must be a bijection between x and y. Finally, the last property, triangle inequality, you have h of x given y plus h of y given z is greater than or equal to h of x given y z plus h of y given z, because conditioning cannot decrease entropy, cannot increase entropy, which is nothing but h of xy given z, which is h of x given z plus h of y given xz. This is greater than or equal to h of x given z, because h of y given xz is greater than or equal to 0. From that you can write rho of xy plus rho of yz is equal to h of x given y plus h of y given x plus h of y given x plus h of z given y. Sorry, this should be plus h of y given z plus h of z given y. H of x given y plus h of y given z is greater than or equal to h of x given z. So this is greater than or equal to h of x given z. Similarly, h of y given x plus h of z given y, h of z given y plus h of, in this entire thing you replace um, x by z and z by x. Then you'll get h of z given x here. This will become h of z given y plus h of y given x, which is the sum of these two terms. And you'll get that is greater than or equal to h of z given x, which is equal to r of rho of xz. So in the sense that if you say x is equal to y if and only if there is a reversible transformation between x and y, then in that sense, rho of x comma y is a metric. Part B you can do as homework. Next we have let x1 and x2 be discrete random variables drawn according to PMFs P1 and P2 over the respective alphabets. Script x1 is 1, 2, 3 up to m, and script x2 is m plus 1 up to n. Let x take the value of x1 with probability alpha, takes the value x2 with probability 1 minus alpha. So here, note that these are disjoint random variables taking values from a disjoint set. A. Find h of x in terms of h of x1 and h of x2 and alpha. Maximize over alpha to show that 2 power h of x1 plus 2 power h of x2 is greater than or equal to 2 power h of x, and interpret using the notion that 2 power h of x is the effective alphabet size. So we'll first define an indicator function theta. So the function of x is 1 when x is equal to x1, 2 when x is equal to x2. We can do this because x1 and x2 have different alphabets, and you can, looking at the value of x, you can tell whether x has taken the value of x1 or x has taken the value of x2. Then we have probability of theta equals 1 is alpha, probability of theta equals 2 is 1 minus alpha. Because x is equal to x1 with probability alpha and x is equal to x2 with probability 1 minus. Now we have h of x is h of x comma f of x. Why h of x comma f of x is equal to h of x plus h of f of x given x. H of f of x given x is 0. So h of x comma f of x is equal to h of x. So that is h of f of x is, then you can write it as equal to h of f of x plus h of x given f of x. In this case, f of x is theta, which is h of theta plus probability that theta is equal to 1, h of x given theta equals 1, plus probability that theta equals 2, h of x given theta equals 2. H of theta is the binary entropy function h of alpha. Is alpha log alpha minus 1 minus alpha log minus alpha log alpha plus minus alpha log alpha minus 1 minus alpha log 1 minus alpha, which is the binary entropy function. Because theta is a binary random variable. Plus p of theta is equal to 1 is alpha. H of x given theta is equal to 1 is h of x1. Because given theta is equal to 1, x is equal to x1. Plus p of theta is equal to 2 is 1 minus alpha. H of x given theta is equal to 2 is h of x2. So if you mix disjoint random variables, that is random variables that take two different sets of values. So there's no overlap between the values that the random variables take. And you mix them in the ratio, mix them according to the factor alpha, which is between 0 and 1. Then you can simply write the entropy of the mixture, h of alpha to be h of x to be h of alpha plus alpha h of x1 plus 1 minus alpha h of x2. So for part B, we have to maximize overall alpha, for which we'll take the derivative of h of x with respect to alpha, d by d alpha of h of x, which is d by d alpha of h of alpha, which is minus alpha log alpha minus 1 minus alpha log 1 minus alpha plus alpha h of x1 plus 1 minus alpha h of x2, which turns out to be minus alpha into derivative of log alpha is 1 over alpha minus log alpha into derivative of alpha is 1 minus 1 minus alpha into derivative of log of 1 minus alpha is minus 1 over 1 minus alpha minus log of 1 minus alpha into derivative of 1 minus alpha is minus 1 plus h of x1. We have to understand that this is derivative with respect to alpha. So h of x1 is not a function of alpha. This is actually h of x1 d by d alpha of alpha, which is 1, plus h of x2 into d by d alpha of 1 minus alpha, which is minus 1. So this term is minus, first term is minus alpha into 1 minus alpha, which is minus 1. And then third term is minus 1 minus alpha into minus of 1 over 1 minus alpha, which is plus 1. First and third terms will cancel out here. So you're left with minus log alpha plus log of 1 minus alpha plus h of x1 minus h of x2. That's d by d alpha, dou by dou alpha of h of x. To maximize h of x, set dou by dou alpha of h of x equals 0. Of course, you will also have to verify whether this gives you a maximum or a minimum by setting it to 0. Do you get? For that, you'll have to take the second derivative, check whether it's positive. If you take the second derivative, what you get is minus of 1 over alpha plus uh, let's see, minus 1 over alpha plus 1 over 1 minus alpha into minus 1, which is minus 1 times 1 over alpha into 1 minus alpha. If alpha is between 0 and 1, this quantity is denominator is positive, so the entire thing is negative. So the second derivative is negative, that means you have a maximum value for alpha between 0 and 1. For alpha is equal to 0 and 1, then it's not really a mixture in that case. If alpha is 0, then x is equal to x2 with probability 1. So h of x is equal to h of x2. If alpha is equal to 1, x is equal to x1 with probability 1. So h of x is equal to h of x1. If it's between 0 and 1, then d square by d alpha square of h of x is negative. So d this by setting d by d alpha of h of x to 0, you get the alpha for which h of x is maximized. Now setting this to 0, you get log of 1 minus alpha by alpha is equal to h of x2 minus h of x1, or 1 over alpha minus 1 is 2 power h of x2 by 2 power h of x1, or 1, you can simplify this, you will just get alpha is 2 power h of x1 by 2 power h of x1 plus 2 power h of x2. Plug in the value of alpha in the formula for h of x. H of x is h of alpha, which is minus alpha log alpha, which is minus 2 power h of x1 by 2 power h of x1 plus h of x2 log alpha, which is log of 2 power h of x1 by 2 power h of x1 plus 2 power h of x2 minus 1 minus alpha, which is 2 power h of x2 divided by 2 power h of x1 plus 2 power h of x2 log of 2 power h of x2 by 2 power h of x1 plus 2 power h of x2 plus alpha h of x1, which is 2 power h of x1 into h of x1 divided by 2 power h of x1 plus 2 power h of x2 plus 2 power h of x2 into h of x2 by 2 power h of x1 plus 2 power h of x2. So here, if you split this logarithm into the numerator and denominator parts, you'll get log of 2 power h of x1 minus log of 2 power h of x1 plus h of x2, right? So the log of 2 power h of x1 part will become just h of x1. And when you multiply it with the coefficient, you'll get h of x1 times minus 2 power h of x1 by 2 power h of x1 plus 2 power h of x2, which is the negative of this part. Similarly, here if you take only the numerator of this log, if you split the log, if you write the log of, right, this, if you say this is log of a by b, you can write it as log a minus log b. So you can write it as log 2 power h of x2 minus log 2 power h of x1 plus h of x2. And again, you will get minus h of x2 times 2 power h of x2 by 2 power h of x1 plus x2, which will cancel out this term, the second term. So only the denominator parts, the first two terms will remain. The numerator parts will be cancelled by the last two terms. So this becomes, and the minus you can minus is outside in the coefficient, and when you split the logs, you'll get minus log of 2 power h of x1 plus h of x2. So we'll get also this here is h of x is less than or equal to, because this is the maximum value. Um, the alpha, this alpha is what gives you the maximum value of h of x. So all other h of x will be less than or equal to. This will be less than or equal to 2 power h of x1 by 2 power h of x1 plus 2 power h of x2 log of 2 power h of x1 plus 2 power h of x2 plus 2 power h of x2 divided by 2 power h of x1 plus 2 power h of x2 log of 2 power h of x1 plus 2 power h of x2. If you simplify this, this is nothing but log of 2 power h of x1 plus 2 power h of x2. If you take log on both sides, the inequality is preserved since log is a increasing function. So 2 power h of x less than or equal to 2 power h of x1 plus 2 power h of x2. So the interpretation is instead of coding the values of x1 and x2 separately using bits, we can reduce the average code word length by jointly coding the values of it. It is so if x is a mixture of x1 and x2, and you want to code, you want to uh, store that information, then instead of writing a code for x1 and writing a code for x2, for which you'll need h of x1 bits and h of x2 bits separately. So you need h of x1 plus h of x2 bits. Instead of doing that, you code for x, you might be able to do better. At least you can't do worse. Question 6. Let x1 and x2 be identically distributed. But not necessarily independent. Let rho be h of 1 minus h of x2 given x1 by h of x1. Part A, show rho is equal to I of x1 x2 by h of x1. B, show rho is between 0 and 1. C, when is rho equals 0. D, when is rho equal to 1. We have rho is equal to 1 minus h of x2 given x1 by h of x1, which we can write as h of x1 minus h of x2 given x1 by h of x1, which is nothing but I of x1 x2 by h of x1. sorry, one more additional step. Since x1 and x2 are identically distributed, the entropy of two random variables depends only on the distribution. So you can write it as h of x2 as h of x2 given x1 divided by h of x1. Now this is equal to I of x1 x2 divided by h of x1. We have h of x2 given x1 is less than or equal to h of x2. Conditioning reduces entropy. But h of x1 is equal to h of x2. Therefore, h of x2 given x1 is less than or equal to h of x1. This implies h of x2 given x1 less by h of x1 less than or equal to 1. Therefore, rho is equal to 1 minus h of x2 given x1 by h of x1 is greater than or equal to 1 minus 1, h is 0. Also, h of x2 given x1 is greater than or equal to 0, h of x1 is greater than or equal to 0, which means the ratio h of x2 given x1 by h of x1 is also a non-negative quantity. Which implies rho is equal to 1 minus h of x2 given x1 by h of x1 is less than or equal to 1. Finally, sorry, this was all part B itself. Part C, rho is equal to 0 implies h of x2 given x1 is equal to h of x1 is equal to h of x2, which implies x2 is independent of x1, which also means x1 is independent of x2. That is, x1 and x2 are independent. Rho is equal to 1 implies h of x2 given x1 by h of x1 is equal to 0, which implies h of x2 given x1 equals 0, which implies x2 is a function of x1. Question 7. Let p of x comma y be given by p of 0 0 is 1/3, p of 0 1 is 1/3, p of 1 0 is 0, p of 1 1 is 1/3. Find h of x, h of y, h of x given y, h of y given x, h of xy, and h of y minus h of y given x, I of xy. So from that table, we have the distribution px as follows. Here is x and here is p of x. X can take the value 0 or 1. When x is 0, probability of x is 0 is summation of p of x by p of 0 comma y over all y. So it's the sum of this row, which is 1/3 plus 1/3, which is 2/3. Probability x is equal to 1 is the sum of this row, which is 1/3. Similarly, we can write y and p of y. Y also takes two values 0 and 1. Probability that y is equal to 0 is sum of that column, which is 1/3. Probability that y is 1 is sum of this column, which is 2/3. From that, we can write h of x is 2/3 log 3 over 2 plus 1/3 log 3, which is 2/3 log 3 plus 1/3 log 3, which is log 3 minus 2/3 log 1 over 2 plus 2/3. So 2 by 3 plus log 3 base 2 bits. H of y is 1/3 log 3 plus 2/3 log 3 over 2, which is also 2/3 plus log 3 base 2 bits. Part B, we have h of x given y and h of y given x. For that, we need conditional distribution. Y is equal to We'll write p of x given y here. When y is equal to 0, probability x is equal to 0 given y is equal to 0 is. So you sum this column and divide each entry in that column by the sum of that column. So you get 1, 0. Here again, you get sum these columns, sum that column, entries in that column, this 2/3, and divide each entry in that column. So you get half, half. That was given y is equal to 1, both x is equal to 0 and x is equal to 1 are equally likely because they have probabilities 1/3 and 1/3. Given x is equal to 0, probability that given y is equal to 0, probability that x is equal to 1 is 0. So probability that x is equal to 0 must be 1. Now similarly, you can write p of y given x. Now you have to sum the rows and divide each entry in that row. Given x is equal to 0, y is equal to 0 and y is equal to 1 are equally likely. And given x is equal to 0, x is equal to 1, y is equal to 1 is certain, and y is equal to 0 is impossible. From that, you can write h of x given y is h of x given y equals 0 plus p of x equals 0, sorry, p of y equals 0 into h of x given y equals 0 plus p of y equals 1 into h of x given y equals 1, which is p of y equals 0 is 1/3. H of x given y equals 0 is the entropy of this distribution, which is 0 because there's no uncertainty there. X is always equal to 0. Plus p of y equals 1 is 2/3 into h of x given y equal to 1 is uncertainty is 1. It's half log 2 plus half log 2, which is log 2, which is 1. This is 2/3. Similarly, you can do h of y given x, and you will get that is also 2/3. These are all in bits because I'm taking log 2. Next, you have h of x comma y is h of x plus h of y given x, which is log 3 base 2 plus 2 over 3 plus 2 over 3, which is log 3 base 2 plus 4 over 3 bits. Part D is h of y minus h of y given x, which is log 3 base 2 plus 2/3 bits minus 2/3 bits, which is log 3 base 2 bits. Let me check if that is correct. Alright, there was a mistake here. This is not plus, this is minus. And similarly, this is also log 3 base 2 minus 2 or 3 bits. It turns out to be 0.918 bits. This is 0.667. So this is minus 2 or 3 plus 2 or 3 log 3 base 2 bits. Which is log 3 base 2, which is 1.585 bits. This is minus 2 thirds, which is 1.585 minus 0.667 is 0.667 is 0.251 bits, and E is I of xy, which is nothing but h of y minus h of y given x, just 0.251 bits. Okay, that's enough for problems from chapter 2. We'll solve a few problems in chapter 3 for the next half hour, and uh, that will be the end of the problem solving session. First, we'll solve a question on Markov's inequality and Chebyshev's inequality. Part A of the question is, for any non-negative random variable x and any t greater than 0, Show that probability that x is greater than or equal to t is less than or equal to expected value of x divided by t. Give an example random variable that achieves this with equality. Part B is on Chebyshev's inequality. Let y be a random variable with mean mu and variance sigma square. By letting x is equal to y minus mu whole square, show that for any epsilon greater than 0, probability that y minus mu greater than epsilon less than or equal to sigma square by epsilon square. Part C, weak law of large numbers. Let Z1, Z2, etc. Zn be a sequence of IID random variables with mean mu and variance sigma square. Let Zn bar be the sample mean of n samples show that probability of Zn bar minus mu greater than epsilon is less than or equal to sigma square by n epsilon square. Thus, probability that Zn bar minus mu is greater than epsilon approaches 0 as n approaches infinity. That is Z1, Z2, the sequence Zn converges to Z as Z is a random variable with mean mu and variance sigma square. Sorry. The sample means Zn bar. That is Z1 bar, Z2 bar, Z. The sequence of the sample means Z1 bar, Z2 bar, Z, etc. Zn bar converges to the mean value mu as n approaches infinity in probability. This is called the weak law of large numbers. This weak law of large numbers is used to prove the asymptotic equipartition property. So the solution, first part goes like this. We have the expected value of x is summation x p of x for all x in script x. You can split this into two parts. X p of x, all x in script x, that is x greater than or equal to t, the summation x p of x, all x in script x, such as x is less than t. Since x is non-negative, x greater than or equal to 0 for all x in script x. Also, from the axioms of probability, p of x greater than or equal to 0 for all x in script x. As for summation x p of x, x in script x, x less than t, is greater than or equal to 0 for all x is greater than or equal to 0, right? Which implies e of x, if you drop the second term, this term is a non-negative term, if you drop it, e of x is greater than, e of x is sum of the first term and the second term. So e of x is greater than or equal to the second term, since the second term is non-negative. E of x is greater than or equal to summation over all x such that x is greater than or equal to t, p of x. Since x is greater than or equal to c, this is greater than or equal to tp of x. This is equal to t times summation of p of x in script x such that x is greater than or equal to t. But summation of our probability of all x in script x such that x is equal to t is nothing but probability that x is greater than or equal to t. It implies probability that x greater than or equal to t is less than or equal to e of x over t. It is the discrete random variable version. So for an example that achieves this equality is x is equal to some value k with probability t over k, 0 with probability 1 minus t over k. It's a binary random variable where t less k greater than or equal to t. Then e of x is k into probability k into t over k plus 0 into 1 minus t over k, which is equal to t. So e of x over t is equal to 1, and probability that x greater than or equal to t is sorry, let me think about this again. All right, this should be x is t with probability k over t, and x is 0 with probability 1 minus k over t, where k is less than or equal to t. Then the expected value of x is t into k over t plus 0 into 1 minus k over t, which is k, and the expected value of x by t is k over t. And probability of x greater than or equal to t is probability that x is equal to t, which is k over t. This is equal to expected value of x over. So that is an example where we achieve the equality. For part B, which is Chebyshev's inequality, we have to let x is equal to y minus mu whole square, so what we do is in part A, set x is equal to y minus mu whole square and t is equal to epsilon square. Expected value of x is expected value of y square expected value of y minus mu whole square where y has the variance mu, y has the mean mu. So expected value of y minus mu whole square is nothing but the variance of y, which is equal to sigma square. The probability of y minus mu whole square greater than equal to greater than or equal to epsilon square is less than or equal to E of x, which is sigma square by t epsilon square. But probability of model phi minus mu is greater than or equal to t greater than or equal to epsilon is equal to probability of phi minus mu whole square greater than or equal to epsilon square. Therefore, probability that magnitude of phi minus mu is greater than or equal to epsilon is less than or equal to sigma square by epsilon square. Then we come to the weak law of large numbers. In part B, set y is equal to zn bar. That is the sample mean. Now the expected value of zn bar, which is the expected value of y, is the expected value of 1 over n summation zi I is equal to 1 to n, which is 1 over n summation expected value of zi I is equal to 1 to n, but all the zi's are IID with mean mu. So this is n mu over n, which is mu. Then the variance of the sample mean is E of Zn by r minus mu whole square which you can write as expected value of 1 over n summation zi is equal to 1 to n as mu whole square expected value of 1 over n summation zi minus mu I is equal to 1 to n whole squared is 1 over n squared expected value of summation of zi minus mu whole squared And since all these ZIs are independent, this will turn out to be uh, equal to expected value of summation of Zi minus mu whole square I is equal to 1 to n. Since Zis are IID, you can verify that yourself. In which case, this is sigma square. Expected value of summation of Zi minus mu whole square is summation of E of Zi minus mu whole square, which is summation of sigma square n times, which is sigma square into n divided by n square will give you in the end sigma square by n. From part B with above substitution, we get probability of magnitude of y minus mu. Here y is z n bar minus mean is again mu greater than epsilon is less than or equal to variance of z n bar is sigma square by n, and we have an epsilon square. Which means that by taking enough samples, that is by increasing the value of n, we can make the RHS go as low as we want. So we can make the probability that is given on the left side come as close to zero as we want. So in the limit, uh, the probability that z n bar minus mu is greater than epsilon is equal to zero. That is the in probability your sample mean converges to the true mean value. So suppose you have let's say you have a biased coin, uh, you do independent tosses, but you don't know the bias of the coin, right? What this says is that if you do enough coin tosses and then take the sample mean, then the sample mean will be as close to the true mean as you want if you do enough samples. So if you do an infinite number of samples, the sample mean will be um, equal to the true mean, from which you can find the bias. So this says that if you have independent trials, independent identically distributed trials, then if you don't know the distribution, don't know the sample mean, then by doing enough number of trials, you will get very close to the actual sample mean. So it's a way to say that you can estimate the sample mean. You estimate the true mean by taking lots of samples and averaging over all the sample values. Okay, that's time is up. So I have solved a total of 8 questions, 7 from chapter 2 and 1 from chapter 3. This is just a sample. There are lots of problems in the textbook. You can solve it yourself. There are solution manuals also available. Maybe you can find them on the internet, which you can use for reference. I hope these lectures are helpful to all you guys.